Anything? Okay. In that case, let's get started. First of all, I'd like to thank you all for being here, and I'd like to apologize for the schedule confusion. So I had to change my plans this morning, and that's why we're meeting this afternoon. The rest of the week, it will be 10 to 11 Central Daylight Time, and I will be here. So first, a couple logistic things. So there, each of the 5 days, I'm going to give an hour lecture, and hopefully there will be lots of questions, so it's not just me talking. What I'm going to do also is probably people are going to have questions, or hopefully people are going to have questions, and so I'm going to try and hang around in the afternoon from 3 to 4-ish. So if there's lots of people, maybe it'll go a little later. If no one shows up, then by 3:50 maybe I'll leave. It'll be the same Zoom room, and I'm going to post some exercises. So the exercises, there are different kinds of exercises, and some of them are you need to do these exercises or you will not understand anything that's going on, and some of them are of the form of if you're interested in thinking about some cool stuff, here's some cool stuff to think about. And these are much more to the latter side. So you can look at them. They should already be on the resources page of the Summer Minicourses website. After the talk, I'm going to post them I'll post them in Slack. I also put up the slides for today's and tomorrow's talks. So, okay, that's logistics. So what we're gonna do this week. Oh, did I not put a week outline? Oops. Okay. So let me say what we are going to cover. So today is going to be generalities, which, okay, well, what is a topological field theory? Maybe a little bit about why, and then sort of the first major theorem of topological field theory, that state spaces are always finite dimensional. The next several days are going to be a series of examples. So Tuesday is invertible field theories. Wednesday is the finite path integral, so Dijkgraaf-Witten theories or things related to that. Thursday is state sums, so the Turiaf-Barrett-Westbury construction. And then Friday is going to be an application, which is using TFT to compute Hurwitz numbers. So I picked this because, there are other introductions to topological field theory out there. And, why did you pick this one instead of, say, reading a book that already exists? And hopefully I can, do something useful that isn't already written down. And existing introductions tend to focus on, for example, dimension 2, where there's the beautiful story of Frobenius algebras. Or they tend to say, all right, we're going to do some higher category theory and talk about the cobordism hypothesis. Or they talk a lot about generalities and don't focus on examples. So I wanted to give a bunch of different examples because it can be hard to construct interesting examples. Or like, there are many interesting examples, but they can be quite hard to construct. And I wanted to show you what that can look like in a couple different cases. And then I want to show an application because, a lot of structuring theory without an application is not as much fun. But that means that we don't have time to do these things. So extended topological field theory. For those of you who like higher category theory, this is where it makes contact with the field of topological field theory. And this is really, when topological field theory appears in physics, it tends to be of this kind. But there's a lot to get into. And so I didn't want to, we're already going to be relatively categorical in it, so I didn't want to get too bogged down. And so it's unfortunate because these are the ones that appear in physics and the classification theorem, the cobordism hypothesis. There's a lot of interesting stuff to say. And I will not say it this week, sorry. Chern-Simons theory is one of the preeminent examples of a topological field theory. And there are some issues with defining it, which personally makes it more interesting to me. But there is a thing there. And Charlie's giving a mini course on that in a few weeks, so stay tuned. And finally, this course is not going to be terribly physics flavored. I'm going to say a little bit. So a lot of things that happen are going to be motivated by physics facts or physics ideas. But I'm not going to talk so much about physics applications, and I'm not going to say a whole lot about like the physics motivation for this definition. I'll say a little, but this is, my intended audience was this is a math course, and the person I sort of envision getting something out of this is interested in the mathematical aspects of topological field theory. I'm happy to talk about the physics related to it, but that might be, for example, in office hours or on Slack some other time. Okay, and here's today's outline. So the way that Atiyah and Siegel formulated topological field theory is as a functor out of a Bordism category. And for some people, this is like everything they've been hoping for. And for some people, they're like, wow, that's words that I wasn't hoping to hear. I just wanted to do mathematical physics. But I think we can get there, without it seeming too unnatural. So I'm going to start by talking about Bordism, and which is this classic question in algebraic topology. And then I'm going to talk about some variants. This construction I think is due to Lashoff. And then once we have those notions in place, we can define topological field theories. And then this is the thing I mentioned about the theorem that will prove that state spaces are finite dimensional. And that should bring us through the hour. Before I go on, are there any questions? Okay. Again, feel free to just unmute yourself and ask questions whenever. So I want to start by just clarifying some terminology. You may have heard Bordism or cobordism. And I think cobordism for a while was the more common word, and I'm going to be using Bordism. So
sorry, Arun, I actually do have a
question.
question. So
yes.
When you say duality, do you mean things like S duality and T duality in physics, or?
Oh man, I wish. No. This is just like dualizable objects in like a symmetrical middle kind of. Yeah, that's this.
Okay.
Yeah, as much as I would love to talk about that, that's pretty far out.
Cool. Thanks.
Yeah, thanks for asking. More questions? Okay, well, feel free to stop me whenever you have one. So cobordism and Bordism. The etymology was cobordism initially meant jointly, it's sort of this Latin root, together, they bound, board. And, but at some point, Atiyah realized that there are two things. There is a generalized homology theory and a generalized cohomology theory. And it makes sense to call the homology theory Bordism and the cohomology theory cobordism. And what we're going to be talking about today is exclusively the homology theory. And so I'm going to talk about Bordism and, and then sort of generalizing Bordism categories. But if you read somewhere talking about cobordism groups, probably they mean the same thing that I do when I say Bordism groups. The point is, don't let this distinction frazzle you. And in the same way, sometimes people say topological field theory, and sometimes people say topological quantum field theory. And in mathematics, in my experience, people use these words interchangeably. But my advisor pointed out that the formalism we're going to talk about, this Atiyah-Siegel formalism, works for classical field theories as well. And so, mathematically saying something is quantum is kind of a funky notion from this perspective. So I'm just going to stick with topological field theory as the technically more correct thing, but you should, these two words are interchangeable as far as I'm concerned, but just reader's guide. So without further ado. So Bordism is this notion that captures when two manifolds that are together the boundary of some manifold in one dimension higher. So you can see in this diagram, there is M, which is a circle, and N, which is two circles. And together they bound this sigma 1, 3, this compact surface. So the precise definition says that a Bordism from, M0 to M1, sorry about that, it must be compact because otherwise this theory gets a lot weirder.
Did he freeze or is that?
Oops, okay, I'm back. I think that was my internet, sorry. Okay, so what I was gonna say is the precise definition of a Bordism is that we pick a compact manifold of one dimension higher, we identify the boundary components with the two manifolds we started with. It's not just there is a diffeomorphism. The diffeomorphism is part of the data. So another feature is this, nothing in this was explicitly asymmetric, but we're saying a Bordism from M0 to M1. And then we say, Bordant is when there exists a Bordism. So Bordism is an equivalence relation, which is why I wasn't super concerned about directionality. Reflexivity is the cylinder. Symmetry is you pick up your Bordism, you turn it around, you put it back down. And transitivity is you glue. So here's a Bordism from M to N. And then another Bordism from N to P. N and P are both two circles. And then you could just glue these because manifolds with boundary, the boundary always has a collar neighborhood. And then you get a Bordism from M to P. And so you know that there is a set of equivalence classes of closed N manifolds up to Bordism. Moreover, disjoint union turns this into a commutative monoid of Bordism classes of closed N manifolds with unit given by the empty set. So this is one of these things where you kind of have to sit and think for a bit about the fact that the empty set is in fact a closed N manifold, vacuously. But let us not be scholars of the empty set. The empty set does what we want, which is it gives us a unit. And then there is a theorem that this monoid is in fact an abelian group, hence the name Bordism groups. Even more structures is here. So there's the direct product of manifolds, and that gives us a Z-graded commutative ring. which is just all dimensions. And I didn't say this in the slides, but just as a thing close to my own heart, these rings have been computed by René Thom in his PhD thesis. This Bordism ring is it's a polynomial algebra on an infinite set of generators, and it's known what manifolds correspond to those generators. But this was sort of a classic problem that people were concerned about back in like the 40s and 50s. Was what is this Bordism ring? Or sorry, what is this Bordism ring? What other variations can we do with this? Before I go on, any questions? Okay, so we're going to spice this up a bit because there's different kinds of things we might care about. So tangential structures are a formalism to generalize the notion of Bordism when you take into account additional topological information. For example, we had our diffeomorphisms of the identifying the boundary of our bulk manifold with the two things we had. But what if we want those to preserve orientations? Then you get a different notion of Bordism and a non-isomorphic Bordism ring. And so tangential structures are a very general way of doing this. I think, like I said, Lashoff was the person to do this. And what we're going to do is we're going to account for topological information. So things like orientation, spin structures. I see a question. Is it easy to give inverses in this group explicitly? Yes, it is. So you see this cylinder up here labeled R. What we're going to do is we're going to take the cylinder and I'm going to take the other end and move it back to the left side. So as far as a Bordism, what that really means is we've partitioned the boundary into 0 and 1. And for the cylinder, we said 0 is one circle, 1 is the other circle. But now we're saying both circles are the 0 boundary. And so what that's saying is for any manifold, this like macaroni is a Bordism from M disjoint union M to the point. So wait, Walid, were you asking about additive or multiplicative inverses? Okay, additive. Yeah, okay, great. Then this is the construction. So so the cylinder, with the correct identification of its boundary components gives you a Bordism from 2 times M to the boundary. And therefore M is for every manifold M is self-inverse. So this Bordism ring is actually an F2 algebra. Okay, yeah, no worries. I'll keep a lookout on chat. And if I miss anyone's messages in chat, someone else who's seeing them, feel free to let me know. Awesome. Yeah, thank you for asking. Are there more questions? Okay. All right. So tangential structures are going to capture topological information. So a spin structure, a principal bundle, a map to a space. But we're not going to take into account geometric information. For example, Riemannian metric, a connection on a principal bundle. You can come up with notions of boundary in these settings. We're just not going to do it today. And also, this is not precise, but information must be local. So in particular, something like a point inside a manifold is perfectly topological, but it's not local. Like you can't, I don't know. Sorry, here's a better example. A CW, yeah. Oh yeah, okay. So a single point inside a manifold is not a local notion. You need to know globally. Like locally, you say there is a point, great. But globally, there could be, if you're just looking around to the horizon, you can't see how many points are on the other side of the horizon. Whereas if you have like an orientation, you have an orientation here, you have an orientation there, you have gluing, you know that they match on the overlaps and you can glue them. CW structures are also a problem because like the N cells, they live somewhere. And so gluing CW structures that you've defined on open subsets is not as well behaved as gluing orientations. And if you're wondering, what does this really mean? Don't worry, this is deliberately vague, and we'll see a precise definition of what tangential structures are, and it'll be fine. Specifically, we're going to consider the stable orthogonal group. So this is the colimit of ON as n goes off to infinity. So what that means is ON sits inside ON plus 1 because Rn sits inside Rn plus 1 in a standard way. And so we have this nice topological group. Therefore, it has a classifying space. So this classifying space is the classifying space for what are called stable virtual vector bundles. And okay, so vector bundles are vector bundles. Stable is saying, or let's do virtual first. So virtual vector bundles are formal differences of vector bundles. So just like you might take the natural numbers and take pairs of natural numbers, a comma b, and think of that as a minus b to construct the integers. We're going to construct virtual vector bundles as formal differences e minus f for vector bundles e and f to x. And then, okay, we say that this is the same as e plus g minus f plus g. So if you've seen K-theory, that this is doing something similar. So stable is saying that I identify vector bundles with, adding a trivial summand, I don't care about that. So so in some sense, that's why going to infinity, that's what going to infinity is doing, is this each step in the colimit is adding another virtual factor or another trivial factor. So homotopy classes of maps to BO is naturally identified with stable isomorphism classes of virtual vector bundles. So this is, I mean, that's kind of very algebraic, but the point is that a manifold has a map to this. And depending on how you're doing this, maybe this is only well-defined up to homotopy, but that's good enough because we have a tangent bundle, and a tangent bundle is a vector bundle on the nose. And so we could, therefore, it is a stable virtual vector bundle. You know, we're only losing information. And that defines a map to this stable orthogonal group, or its classifying space. And so the point is this exists. Great. Now what we're going to do is we're going to say, so, sorry, before we do this, let's suppose that we had an orientation on our manifold. Then you could do this whole thing with oriented vector bundles, you know, stable virtual oriented vector bundles. And that is the classifying space of the stable special orthogonal group, the colimit of SON. And so it is true that a manifold admits an orientation if and only if the map to BO factors through BSO. And the different orientations of M are parameterized by choices of lift that are not homotopy equivalent in this through lifts of the tangent bundle. So we're going to generalize this vastly. We're going to say, okay, you know, we had a special space, BSO, that told us something geometric, orientations, or, well, topological. But let's just say, let's pick any space and any map to BO. Okay, well, it has to be a fibration, but up to homotopy, you can make any map into a fibration, so we're just going to forget about that. So I'm going to define a Xi structure as a lift of the stable tangent bundle from as a map from BO to a map to B across Xi. And then, you know, there's a space of these, and we want the path components to be equivalence classes of Xi structures, which is why there are, you know, H0 many orientations rather than infinitely many. So yeah, okay, great. I'm going to give some examples, and then I'm going to check that everyone's happy with the definition. So one key example or one key family of examples is, let's say you have a family of maps Gn to On. Then you can stabilize and take the colimit and obtain a Xi structure. So for example, for SON into ON, this is an orientation, and for spin n into ON, this captures the notion of spin structure. You may have seen the notion of spin structure defined differently, especially in low dimensions, but this is equivalent. And you may have seen this definition given more geometrically. I always feel like I have to look over my shoulder when I give this flabby homotopical definition, because there's a more precise definition in terms of principal bundles for this, where you say, it's a reduction of structure group of the frame bundle. And that perspective is much more helpful in geometry, but we're not, you know, we're doing topological fielding. Are there questions about tangential structures so far? Okay, well, when you have questions, of course, do not hesitate to ask. More examples, good. So these have a slightly different flavor. One thing I could do is I could take BO cross BG, where G is some other group and BG is its classifying space, and just project down onto the first factor. In this case, a tangential structure, or sorry, a Xi structure is equivalent to a map to BG. You know what has to happen on BO because it's the, you know, that part is determined because we have to restrict to the tangent bundle. And a map to BG is equivalent data to a principal G bundle. So this tangential structure gives you principal G bundles. And then more generally, BO cross X as a tangential structure encodes a map to X. And so equivalence classes would be homotopy classes of maps to X. So question.
So is there any difference between working with principal G bundles as you wrote versus just with a map to BG? Is there something we gain from keeping track of BO?
So the formalism is that that BO is keeping track of the tangent bundle. So we want to so later this is going to involve Bordism invariance of manifolds of the principal G bundle, right? And so the advantage that keeping track of BO gives us is we can do things like take characteristic classes of the tangent bundle plus characteristic classes of the G bundle and use those to define Bordism invariance. So it just gives us a little more legroom rather than forgetting about the tangent bundle.
Okay, thanks.
Yeah, great.
I had a quick question too.
Yes.
Can you do something similar in the cotangent bundle?
Yes, you can. So a lot of what's going on here is pretty insensitive to the tangent bundle, like things like this. So if you pick a Riemannian metric, that defines an isomorphism that defines an isomorphism from the tangent bundle to the cotangent bundle, right? Yes, I think. Yeah, I think that's right. And so the map you're going to get is the same up to homotopy. So asking when does the cotangent bundle have a spin structure is equivalent to asking when the tangent bundle has a spin structure, or for any tangential structure. So yeah, I like this question. This is a good question, but you don't end up getting you end up getting basically the same notions.
That makes sense.
There is, however, there's a thing called the stable normal bundle, which is you say you embed your manifold in a very large sphere, like high dimensional sphere, and then you get a different vector bundle called the stable normal bundle. And so notions of stable tangential structure and stable normal structure are related but slightly different. So that's another way of thinking about it. More questions? Okay. So the key thing that we want to do for this, because Bordism, is we want to induce a structure on the boundary, because I want to make sense of when, given psi structures, what is a Bordism between psi manifolds. So on a manifold with boundary, the tangent space of the boundary, the tangent space of the boundary is stably equivalent to the tangent space of the bulk. Why is this? Because the inclusion of the boundary, the tangent bundle splits as the tangent space of the boundary plus the normal bundle. So you can see here is a section of the normal bundle. And the normal bundle is trivializable. You can think of this as you walk, like you pick a metric and then you just walk like distance epsilon into your manifold, and that's your section. And that the normal bundle is a line bundle, so you get a trivialization. However, you could have also walked off the manifold in distance epsilon, and you're thinking I can't actually do that, but infinitesimally when it comes to different, like the tangent space is still a vector space, you can still walk in that direction. So these are two trivializations and they are inequivalent. Therefore, let's say I have a psi structure on M, on the tangent bundle. Then because if you trivialize the normal bundle, then the tangent bundle of the boundary and the tangent bundle of the bulk are now stably equivalent on the boundary. And therefore, a psi structure on the bulk induces a psi structure on the boundary. So that is how we're going to define Bordism, but it matters which trivialization we took. We're going to say boundary of M means that we refer to it with its inner unit normal trivialization, and minus that to refer to the opposite one, the outer unit normal. So just to ground your intuition, if you are doing this for orientations, which is sort of the case that everything is based on for this general formalism, then these two will have opposite orientations. So it's like the two different orientations on the boundary that you might have seen in a Diffeomorphism class. So okay, you saw this picture. Here's the inward normal vector field. So this would be the one that we're calling M, not the one we're calling minus M. Yeah, okay, here. So you can see that. So in particular, what's going on the cylinder? So on the cylinder, on one side we have the inward normal, and on the other side we have the outward normal. Like we could have picked both, but the point is that the cylinder with the usual vector field is a Bordism from M to minus M if we're keeping track of these trivializations. So the reason this is important is because when we define Bordisms of psi manifolds, we now care about that minus sign. We say that a Bordism is it's a psi manifold that's compact of one dimension higher. All things have psi structures, and the Diffeomorphisms identify the psi structures. But now we say that one side I have the inner normal, and the other side I have the outward normal. So this is needed to make the theory like, yeah, I think this makes transitivity better. So this again gives an equivalence relation compatible with disjoint union And so we now get Bordism groups, and they're denoted omega n psi for n-dimensional psi manifolds up to Bordism. If this is your first time seeing this stuff, then thinking through this example is a good one to do. Like, okay, well, why is it reflexive, symmetric, transitive? Just a little bit carefully, although not in obscene detail. And if it's not your first time seeing it, then okay, you know why it's true. However, it is not true. This one is harder to think through. So I'm not saying that you need, if you want to think about it, great, but it's harder to come up with these examples. It is not always true that we get a graded ring. You can pick explicit examples of tangential structures where you just don't get a graded ring. So for example, there's two different pin groups, which are unoriented analogs of the spin group. And you get the two notions of Bordism, and neither of them is a ring. Okay, before I go on to Bordism categories and topological field theory, that's the change of subject. So let's see, I'd like to pause for questions again and see if anyone has any. I promise I'm pausing for questions because I want to hear your questions, not just because I want to drink tea.
So I'd like to ask, with the minus sign, so these two bundles have this is isomorphism, right? But have the different orientation.
Yes, precisely.
But how to define two orientation is isomorphism or not?
So actually, I guess the way I would think about that, in some sense, I don't really care whether minus n is the same thing as n when making this definition. In some psi structures, it is. And there are some manifolds. So like the two-sphere, you can reflect across the equator. And so that exchanges the two orientations. So sometimes, so the way that I would say the right notion of like orientations being equivalent, is there a diffeomorphism, which sends one orientation, like pulls back one orientation to another. So the reflection, you start with one orientation and you end up with the other, so they're equivalent. On some manifolds like CP2, you cannot get from one orientation to the other via a diffeomorphism. Did that help answer your question?
Yeah.
Okay, cool. More questions. All right, I'm going to carry on. So we're going to upgrade this structure, and it's part of the general form of categorification, where you replace maybe numbers or with sets or vector spaces with categories, and so forth. We're not doing this just because, but the point is, some of the intuition that builds the Bordism category, Bordisms and like thinking about Bordism groups that we use in the first half hour, is going to come back again to define the Bordism category. And then we're going to use Bordism groups themselves tomorrow. So the idea is that it's not just that Bordisms are an equivalence relation. You can think of a Bordism as a map, like a morphism from the beginning manifold to the ending manifold. So what we're going to do is we're going to say that literally. We're going to say that make a Bordism category whose objects are closed n-1 dimensional manifolds with psi structures, and whose morphisms are structured Bordisms between them. So the asterisk is we need to take diffeomorphism class's rel boundary of Bordisms. So in other words, if two Bordisms are diffeomorphic, we just say they're the same morphism. This is so that composition is associative on the nose. If you like infinity categories, you can work around this, and that is all that I'll say about that for now. So the identity is the cylinder, which is why it's crucial that we said m to minus m. The cylinder is a Bordism from m to minus m. And so in order to have an identity morphism in this category, we have to define Bordism with this minus. And then composition is gluing. So, okay, wait, yeah, that's the definition of Bordism category. We get this additional structure. So a lot of times when you're categorifying, you should ask, this extra algebraic structure I have, does it manifest on the categorical level? And here it does. That disjoint union and the empty set, again, they form a notion of a commutative monoid structure on the Bordism category, except it's in like a categorical sense. And this is called a symmetric monoidal category. And so what this means, there is a definition that you can read in McLean, which is right here, as it happens. This is not my copy. I think it's a friend and I need to return it to them. But there is the definition of a symmetric modal category is essentially saying I have a tensor product, which is associative and commutative up to natural isomorphism, and I have a unit, which is a unit up to natural isomorphism. You know, the kind of thing that always appears when you do categories is that conditions become data that you have to account for. And then there's a bunch of conditions that these serve. So for example, associativity, you define an associator, and then there's a bunch of stuff that makes it work. I am encouraging you to not read the definition until you need it. But the point is, it's something which has associativity and commutativity up to natural isomers. For example, complex vector spaces, or any vector spaces, and tensor product. And manifolds up to Bordism and tensor product, which is disjoint union. So, so the point is the unit is the empty set, and the symmetric monoidal structure is disjoint union. Somewhat like in vector spaces, the unit is C, and the tensor product is tensor product. So likewise, you can come up with notions of symmetric modal functors and symmetric modal natural transformations, and I will encourage you to read about that in the book that says it. And but you can think of these as preserving the structure, even though more has to be said. So that's that. And now, the moment we've all been waiting for. So a topological field theory is a symmetric monoidal functor from the Bordism category to the category of complex vector spaces under tensor product. This is a very compact way of saying an extraordinary amount of information. And so, especially because, you know, when I first read this definition, I was not so category minded. So let's unroll some of this stuff. So in this category, the objects are closed n-1 manifolds, and the Bordisms, the morphisms, are n manifolds. So n is called the dimension of the theory. Oh, geez, this is a bad typo. Let me be super clear. The dimension of the theory is n, and if you need to clarify, the dimension of the morphisms is the space-time dimension, and the dimension of the objects is the space dimension. So this n should be n-1. I'm really sorry about that. This is like the worst possible place to make a typo. So, so this is sort of like if you, in physics, you might think of, well, okay, there's interpretations of the Bordism category where your objects are space, and then the morphism between them is like time evolution, so you get space-time, which is kind of a wild, it's kind of a weird thing to think about, but it is some of the intuition that's going on here. Did I say, okay, I'll say a little bit about why. So what is this data, the symmetric monoidal functor? What does it buy us? So for a manifold in space dimension, closed n-1 manifold with size structure, Z assigns a vector space, and this is called the state space. So if you're used to thinking about quantum mechanics, there's like a Hilbert space of states that you, and in quantum field theory, you're saying, let's do that on arbitrary manifolds. And that's what this is doing, is on a manifold in the space dimension, so codimension 1, you're getting out a Hilbert space. Here, everything, we're going to see why we don't, in a little bit, why we only have to think about finite dimensional, and therefore topology is not a question. And so we get, we're just going to get a vector space rather than thinking about anything else. And again, if you are used to thinking about quantum mechanics, where there's like a vector space of states, this is doing something similar. So a Bordism from M to N defines a map from the state space on M to the state space on N, and it's linear. And then functoriality means gluing goes to composition. Functoriality is a very big word for this concept, that you get, that Bordisms give you these linear maps, and that gluing behaves as it should. You can think of this as time evolution from states on M to states on N. The topology is changing, and this will deeply unsettle some of the physicists. And I'm sorry, we can talk more about physics motivation later. So another important piece of jargon is, so Z of the empty set is C. This is guaranteed by symmetric modality. 1 goes to 1. So on a closed N manifold, so space-time dimension, so that is a Bordism from the empty set to the empty set. So it is a linear map from C to C. That is equivalent data to a number, which is the image of 1. And that is called the partition function of X. So that is a quantity that if you are a quantum field theorist and you're studying a particular quantum field theory, that's a thing that you want to know. And so here is how it falls out of the functor.
Wait, Arun, what was supposed to upset the physicist?
So when I say physicists, I mean that my friend Ivan Tully told me that he didn't like the idea that time evolution should change the topology of the manifold. So so as far as he's concerned, the best Bordisms are cylinders. And so when you're doing this weird stuff, like, you know, the universe isn't like bubbling off other pieces of space while we're like looking, as far as we can tell. So calling this physics might be a little bit weird. But there are different situations in which you might care about the topology changing. I think quantum gravity has this, and also like in math, it's okay. But I remember, you know, there are lots of people who think, well, you guys are doing good math, but is it really physics related? Phase transitions is a good question. Someone asked me about that at lunch today. I wish, okay, I love this question, and I wish I had a better answer other than those seem to be similar, and I don't know much more about what I just said. Oh wait, David, you had a question that I missed. Sorry. David, do you mind if I ask what context your partition function is in? Is this like a StatMech thing?
Yeah, I was thinking about like the only one that I understand well is like the 1 and 2 dimensional like easing spin chains. Yeah.
Okay, well, hopefully that's been easing you into the theory really nicely. No, but seriously, this is not quite related. Like they're both doing a similar thing. My best understanding of the physics is that easing is kind of classical, and that the partition function in quantum field theory is related, but they're not exactly the same. And then this is similar to the partition function in quantum field theory. It is true that you are that there's a sense in which you're summing over configurations in some in important examples of topological field theories, the partition function, like Dijkgraaf-Witten theory, the partition function is a sum over things. So I think the answer is yes, that is often correct, but there's not like a general theorem.
Okay, thanks.
Yeah. Ooh, okay, Surya has a good answer. So with regards to, there's this question, sorry, I don't know how to pronounce your name. But your question about how does the empty Bordism send to the complex number? So sorry, it's the empty manifold, not the empty Bordism. So the empty manifold is an n-1 manifold, and it is so a topological field theory sends it to some complex vector space. The fact that this is symmetric monoidal means that the unit, so the empty set is the unit for the symmetric monoidal structure, because disjoint union with an empty set doesn't change anything. And because a TFT is symmetric monoidal, it must send the empty set to the unit in vector spaces under tensor product. And that is the complex numbers. Did this help answer your question? Slash, are there more questions here?
I have a question, Arun.
Great, yeah.
So your symmetric monoidal functor, I guess, is what I might call like a strong symmetric monoidal functor.
Yes, yes.
So
good.
There must be some sort of physics motivation for not considering, say, like lax monoidal functors. Is that right?
Yes, I think so. So I think the reason lax is where you just have a map between the two, right?
Right. So like lax is like, yeah, I never remember. It's just like exactly what you need to preserve monoids. So like strong is like a little bit more.
If I'm remembering correctly, because I don't know the definition of lax either, strong is like what I want is the disjoint union, the state space on a disjoint union to be isomorphic. So the tensor product of the state space is here. And lax is saying there's a natural map between them. Mm-hmm. So quantum mechanics considerations say that if you have, this is something someone told me, so I'm not super sure like about the details, but if you have quantum mechanics systems that are kind of separated and don't interact, the Hilbert spaces of states are tensor products of the two. And so we're trying to imitate that rather than saying, we want to map from the tensor product into something else.
Yeah, okay.
There is some, I've seen a couple papers about lax TQFTs where you say what do you get if the functor is lax monoidal? And the person I'm thinking of, it was they did a PhD thesis a couple years ago, and they're doing a couple follow-up things, and they're using it to do some stuff in algebraic geometry. I don't remember any. Let's see if I can find it. But it's something, yeah, so people think about that. It's just not nearly as common. Great, did that answer? Wait, are there more questions or follow-up stuff?
Sorry, I just, hi Arun. I just wanted to make a very quick comment in response to David's question from earlier about the connection to partition functions in physics. I mean, yeah, morally, the thing is the context that you're talking about is really one in which the Hamiltonian is literally zero. right? In which case
Yes.
we don't actually have a spectrum of states of differing energies. The situation that I think David had in mind is one of a more general quantum field theory, in which, say, you can compute the partition function on a manifold of the form some spatial manifold times an S1 with some finite length, in which case that thing actually has the physical interpretation of evolving in Euclidean time by an amount which is equal to the length of that S1, in which case you will in fact get an expression of the form of a statistical sum of e to the minus beta times the energies, where beta is the length of the S1. But that's a more complicated setting than the one that you have in mind.
Right. Yeah, that's the advantage of the topological setting, is like when your Hamiltonian is 0, some things that you had to think about, you don't have to think about. But the intuition for the non-topological setting is just generally a good thing to have around. Yeah, thank you for the explanation. Just to make sure that we get through everything, I'm going to go on, but please keep asking questions. And worst case, there's Slack, and also I'll be around afterwards to talk about questions. So, I think it's important that we have examples. So this example is really silly. What we're going to do is but it is in fact a topological field. So what we're going to do is we're going to assign to every codimension 1 manifold, so in space dimension, we're going to assign it the state space the complex numbers, canonically the complex numbers. Now to every Bordism, we're going to assign an exponentiated Euler characteristic. So you pick a scalar. Oops, this n should be capital. And you define the relative Euler characteristic as the Euler characteristic is an alternating sum of ranks of homology groups. And what we're going to do is we're going to do relative homology groups. So this has a nice gluing formula because it's just, it's just counting with a sign, it's counting cells of your CW structure. And so formulas for the Euler characteristic of a disjoint union or a gluing tell you that this is in fact a symmetrical nodal functor, this assignment. So this is the first example of a TFT. It is somehow not, it is one of these things which for lambda not equal to 1, it is not trivial, but it's almost true. So the last part of this lecture is going to be proving a theorem. And what we're going to prove is that the state spaces, Z of M, are always finite dimensional. And this is just a, so why this? This is a good generality to have about topological field theory, just because it's a major way in which it differs from quantum field theory, where state spaces tend to look a lot more like L2 of something. And also it'll get, it's a tool that like how, well, it's a shadow of other ways in which people work with topological field theory that are good to know. So how are we going to do this? It's going to be kind of, we're going to work with a notion of finite dimensional. So you know what finite dimensional means for vector spaces. That is like the first thing you learn. And it turns out you can recover a notion equivalent to finite dimensionality by only knowing the symmetrical nodal structure. So you can define it using tensor properties. So therefore, we can generalize this definition to arbitrary symmetrical nodal categories, show that finite dimensionality is preserved by functors, symmetrical nodal functors, and then showing that everything in board N is finite dimensional. So that's the proof strategy. So first, there's this notion by Dold and Puppe that is duality in a general symmetrical nodal category. So duality is saying that I have a dual and two morphisms. Ah, crap, this E should be an X. So X tensor X dual to 1 and 1 to X tensor X dual. And these are called evaluation and co-evaluation. You should think of evaluation as like the evaluation pairing on the dual of a vector space, V tensor V dual, take a vector and a covector and pair them together. So then you have two maps and they must compose the identity. I'll show you a little more intuition for how these work. But you have this data and these conditions, and then you say X is dualizable, and you talk about the dual, the evaluation, the co-evaluation. So typically, people draw these string diagrams. So evaluation you can think of as like time goes this way. So you're taking X and X dual and you're sort of colliding them. In co-evaluation, maybe you're birthing something new, X dual and X. And the two conditions that we had are encoded in what's called the S diagram and the Z diagram, which is that if the straight line is the identity, then this composition reading left to right is the identity. And likewise, the Z diagram, this composition left to right, is the identity on X dual. So this makes it a little easier for me to just like think about like those maps. Any questions yet?
Yeah, I looked away for a moment and missed the statement of the theorem. What are we proving about Z of M again? Oh, finite
Finite-dimensional. Yeah.
Okay, great. Thank you.
More questions?
How do you differentiate between X dual and X here? Do you have an orientability on this interval somehow?
So this is just abstract. Like right now I'm not trying to do anything precise. Like this isn't one-dimensional TFT, although it could be if you put orientations on everything, good. But this is just, here is a picture of the S and Z diagrams that may make it easier to remember how they look. Like, because, you know, this is just like, okay, well, where is X dual? Where is X? Where is E? Where is C? You know, but this is telling you what, like, this is telling you what those conditions really are, if that makes sense.
Thanks.
Yeah. Yeah, sorry, that was kind of a non-answer. So the first example we're going to talk about is vector spaces. So suppose that V is a dualizable vector space. Now, co-evaluation sends one to some element of V dual tensor V. And just because of the way tensor products work, this is a finite sum of elements V upper I tensor V lower I. Now, you can wind this through the Z diagram and conclude that for any X, you get this relation, that if you evaluate X, this is sort of a, what's it called, Riesz representation theorem, that if you evaluate X and VI on a V upper I on sort of the dual V lower I, and then you sum those together, you get back X. And this has the consequence that the finite set V lower I spans V. Therefore, a dualizable vector space is finite dimensional. Correspondingly, given a finite dimensional vector space, then what do? You take the standard dual vector space, and E is the evaluation pairing that I mentioned. Co-evaluation is harder to define canonically. You can take any basis in the dual basis and then just say E upper I tensor E lower I and sum. You could also say that V dual tensor V is naturally isomorphic to end of V, and then pick the identity, and that's sent to this under this identification. So finite dimensional vector spaces are dualizable. Note that if you picked, okay, great. And now in board N, every object is dualizable. So given a, this is the circle, but you can do this for anything. Given a circle, evaluation is the outgoing macaroni, and co-evaluation is the incoming macaroni. So you can see these two macaronis as part of this thing. And the S and Z diagrams, well, we take diffeomorphism classes of Bordisms as our morphisms. So this Z morphism, which is the Z diagram in board N, is the same as the identity. And then the same thing for the S diagram. So David Ben-Zvi likes to call this Zorro's lemma, because you imagine the swordsman drawing the Z, to complete his proof. And also, I mean, I think that's just a colorful creative name, and more theorems should have colorful creative names. So please join me in calling this Zorro's lemma. And so we know that all objects of board N are dualizable. So now let's go back here. If I have a symmetric monoidal functor, then it preserves duality. The image of a dualizable object under a symmetric monoidal functor is still dualizable. Why is that? Because you say Z of X dual is, you define the dual of Z of X to be, sorry, Z of X dual. The symmetric monoidal functor factors over this tensor product. So we get evaluation co-evaluation maps, and it must send the identity to the identity. So, and I said this poorly, sorry, but the point is that if you hit the definition with a symmetric monoidal functor, you're going to again obtain a dualizable object. So therefore, if X is dualizable, so and F is symmetric modal, F of X is dualizable. And therefore, now we prove the theorem. Given a topological field theory and an object in the Bordism category, we know that the object is dualizable because Zorro's lemma. And therefore, Z of M is dualizable in vect, and therefore it is finite dimensional. And that's the theorem. So are there questions about the proof of the theorem or anything, in fact? Okay, I'm going to go on. I'm going to make sure I don't go over time, but I have a little more prepared. So this is another general feature about topological field theories, which is occasionally useful. I'm going to focus on unoriented, so O, or oriented, SO field theories. It is possible to do this in more generality, but these are the most commonly considered cases, and doing it in generality can be a little bit annoying. Like I remember last time when I did this course on a chalkboard in 2019, getting confused. And so I think there may be some things in the lecture notes that are just wrong. But here, I think everything on the slide is correct. So the key idea is, as a feature of the Bordism category, the Diffeomorphism group of M acts on the state space by mapping cylinders. So we can define, I told you it matters the data of the identifications in the Bordism. And so let's define a mapping cylinder by taking the cylinder Bordism, but attaching M at 0 by the identity, and at 1 attaching it by our Diffeomorphism. So this is not equivalent, because I said Diffeomorphism is rel boundary when making associativity work. This is not always the same morphism. So, but this defines a group homomorphism from Diffeomorphisms to the automorphisms in the Bordism category of M. And therefore, by functoriality, we get out an action of the Diffeomorphism group on the state space, which is just the image of this mapping cylinder under Z. Now, it turns out, if you take two isotopic diffeomorphisms, then their mapping cylinders are diffeomorphic rel boundaries. They define the same morphism. And so the diffeomorphism group action factors through the action of what's called the mapping class group. So diff0 is the connected component of the identity, and the mapping class group is what remains. So for example, the diffeomorphism group of the torus is this infinite dimensional terrible thing, but the mapping class group is XL2Z. So here I want to say, sometimes people assume that diffeomorphisms or mapping class group actions are like implicitly only the orientation preserving ones. But what comes out is what your notion of TFT said. So if you care about oriented TFTs, you get out the oriented mapping class group and the oriented diffeomorphism group. For unoriented TFTs, you get out unoriented and unoriented. For spin, you get out spin, and okay, so on. So this is just a thing that appears that is kind of nice and interesting. Sometimes it's useful, but not super often. Here's a last thing that you can just do generally. So I mentioned a mapping cylinder where you attach in two different ways, but now let's identify again, and we obtain the mapping torus. So this is the interval cross M, modulo, where I'm, instead of making the identification 0x to 1x to get S1 cross M, I rotate one of the identifications by phi. And that is a manifold called a mapping torus. And it's possible to show, and this is one of these I think this is one of these relatively straightforward hands-on things, but I'm scared because I haven't looked at the proof in years, so I could be very wrong. But I think it's not too hard to show that the partition function of a mapping torus is the trace of the action of this diffeomorphism on the state space. And the special case is that the trace of the identity, so the mapping torus of the identity is M cross S1. And the trace of the identity is also known as a dimension. So this is just a general fact about, this is dualizability hiding again. The fact that since it must be defined on M cross S1, then this number must be finite. Okay, I have reached the end of my slides for today. So I guess I will stop and then ask for questions. First with the recording on, and then after that, I'll ask again once the recording's off in case people have questions they might feel apprehensive about asking on the recording. And then I'll stick around a little bit for office hours for maybe an hour or so. And after that, it'll be see you tomorrow. So let's see. Are there questions? Please ask questions.
This is sort of a random question just to get it started, but these Euler characteristic theories that you defined earlier, are these the only ones that are tensor invertible up to being strictly equal? Like they don't have a, normally when we say invertible, we mean has a copy of the trivial object, but here I mean just is isomorphic to the trivial object.
Wait, so invertible for you means Z tensor Z inverse is trivial, not Z tensor Z inverse has a trivial sum in?
Well, I know that's normally what we mean is the latter, but
so to me, invertible means what you said.
Oh, really? Okay.
Interesting. Wait, okay. No, this is good to know so that I don't get myself in hot water. Thank you.
Oh, I mean, I guess I just mean like when I talk about like invertible objects in a just like a fusion category. Normally, I mean, has a one summand.
Oh, interesting. Okay.
Yeah.
So yeah, so when you refer to invertible objects in a symmetrical category in general, what I thought was standard, and I'm going to have to go back and double check, is Z tensor, some other theory, Z inverse, is isomorphic to the trivial theory. Nothing else in it. And in that case, as you notice, the Euler TFT is invertible, and the inverse is the one for lambda inverse.
Right.
But there are other examples, and this is actually this. So I'm going to talk all about that tomorrow. In fact, the gist of it is you basically. Roughly, you get the Euler TFT, and then TFT is built out of Bordism invariants. And so some homotopy theory goes into this, which is, therefore something I think is very cool. But I think when I'm going to explain it tomorrow, I think it's going to be hopefully not too out there. But yes, there are other good examples.
Thanks.
Yeah, good question. Who else has questions?
Aaron, I was wondering, so earlier you defined Bordism groups. Is there a way to like formally get them out of the Bordism category? Kind of like a Grothendieck group construction, but that wouldn't work.
Yes. So let's take. Yeah. So this is also going to come out tomorrow, actually. So one thing you can do. So you just have this abstract symmetrical modal category. Like secretly, it's the Bordism category, but maybe someone handed it to you, and you're not sure. So one thing you can do is you can take the so pi 0 of this, so that the set of isomorphism classes of objects under disjoint union, that is a commutative monoid. Do we need to? Yes, that is a commutative monoid, and you can group complete it by sort of formally adding inverses. And when you do that, you get omega n minus 1. So you can recover the Bordism group from the Bordism category that way. However, in top dimension, you don't get omega n. You get something different. And we'll talk all about that tomorrow. You get a different notion of Bordism. But in short, to answer your question, you can recover the n minus first Bordism group from the n-dimensional Bordism category.
Thanks.
More questions?
Can you say more about why the Hamiltonian is 0 in the cases that you're discussing today, or just give some more intuition there?
Sure. So, yeah, so the problem with that, and so the disclaimer before I say it is, the Hamiltonian is not part of this data of this functor. So this is sort of when people talk about this, at least when I talk about it, it's sort of an intuition for how I think about what's happening on morphisms. So usually people talk about in like Hamiltonian quantum field theory that the cylinder of length t is time evolution for time t. And so, sorry, I lost my train of thought. Yes. So the point is that if what that is on the Hilbert space is you exponentiate t times the maybe minus t times the Hamiltonian, and that tells you your time evolution. So in some sense, you have a Bordism category of manifolds and cylinders, but the cylinders have a length, and that tells you and the length sees part of the Hamiltonian because time evolution is non-trivial. Now in topological field theory, all cylinders are the same because we don't know what length is. And so the only way for that to make sense, for e to the minus t times your operator to act as the identity, is for your operator to be 0. So when people say the Hamiltonian is 0, that's what's going on here.
Okay, great, thanks.
Yeah, good question. Are there more questions? Okay, in that case, I am going to stop the recording.